It's great to finally make it to Israel. Lots of people contributed to this. These two characters are from your wonderful institution. So I've been working on optimal control for a while and trying to make sense of biological movement, starting with the high-level idea that there is something the organism cares about and it wants to do it in the best way possible, and every detail we see comes from that high-level principle. And as most people in this field, I started with looking at a point mass moving in the plane in 8 different directions usually, because that's what Georgiopoulos did at the time, and we got stuck with it. If you decide to be slightly more detailed, you might imagine an arm with a bunch of muscles behind it, and then the movements tend to become somewhat curved, and a number of people have done that. At some point, I guess I got an early midlife crisis, and I realized that I'm too old for this. And it's really time to start looking at human movement itself and not at some sort of cartoon description of it. So now everything I do is done under the constraint that it has to work for large-scale movements, and if it doesn't, I don't care about it. As a scientific principle, you might worry that, aren't we supposed to start simple? And two answers to that. One, we already started simple about 100 years ago. Time to move on. But also, keeping it simple can be a mistake, specifically when you study the brain, because there are too many seemingly good ideas that are good on toy problems, and they don't scale. They don't really solve the large problems. And the few of them that do scale, but they're hard to identify if you study the simple problems, and you may even discard them because Occam's razor tells you to do the simplest possible thing that makes sense, and if you work on toy problems, the complicated algorithms don't make sense. So in this talk, I'm going to talk to you about a number of algorithms we've developed recently that have been able to scale surprisingly well, and I'll tell you how they work, and towards the end, I'll talk a little bit about what they may have to do with the brain, but be warned that this is more of an engineering, computer science, robotics, numerical optimization talk, and I mostly leave it as an exercise to the audience to decide what it has to do with the brain. So the primary tool that we've been using is something that initially I was somewhat skeptical about, but it turns out to work really well. It's called trajectory optimization. So what that means, what is a trajectory? Trajectory is a sequence of positions over time. If you differentiate it, you can also compute velocities and accelerations. Normally, we think of trajectories as emerging from the interaction between the physics and biomechanics and some sort of feedback control system in the brain. But here, we're actually going to think of the trajectory as being the primary object for the time being. And we're going to optimize them directly. So the way this game works is that you have a black box that has lots of math and lots of code based on it, and it's small, so you don't read the details. And the 3 inputs to it, one is the physics model. You have to model the thing that you're trying to optimize. You can also try to do model 3 things, but they're one of those ideas that they look good on paper, and you try to scale them, and you realize that's not so good. You have to specify what is that you're optimizing, the cost or objective function, and also are there any hard constraints that you're willing to impose, or do you want to put them in as soft constraints and mix them up with the primary cost? And you usually have to choose how you are going to parameterize the object that you're searching for. It could be just a sequence of positions over time. It could be some sort of splines or polynomials. Well, splines are polynomials. Or other things. Here's one example that was done by Tom Ayres. So this is from first principles generating human locomotion. So here the physics model is what you see. The cost function says move the head forward at a predefined velocity and minimize energy, and that's it. Do whatever you want. Okay? And that's what comes out of it. So here, because we knew the motion is periodic, we picked a representation that helps that. So we represented joint angles in a Fourier basis with a certain number of components. And you could have done it differently, but the point is that you can get very rich, very realistic looking behaviors from surprisingly simple cost functions, as long as you model the physics. Now, we've gone through a number of algorithms over the years that have different strengths and weaknesses. The one that has proven to be the most powerful is something we call the contact invariant optimization. It's abbreviated CIO. And this algorithm was developed to address a big computational challenge, which is that if you look at what do animals do on land, not swimming or flying, but actually living on land? Well, what they do is mostly they make contact with the environment. And pretty much every movement you make, except for things like eye movements, serves the purpose of making contact with something in the world and producing forces on it. For example, when you walk, you plant your foot so that you can push on the ground and not fall. When you reach an object, you don't reach because you like reaching. The only reason you reach is because you want to grasp it and do something with it, etc. Contact dynamics are inherently discontinuous, which makes them incredibly difficult to plan through and kind of see the future through them. And in general, if you consider this little cartoon here, so suppose this character wants to get up on this surface. The red objects are the things that are in contact with the environment. And you see in different phases of the movement, there are different parts of the body that may be in contact. So as you would imagine, this is some kind of piecewise continuous optimization problem that's punctuated by these changes in contact state. But the problem is that in general, there could be a combinatorial number of them. Like imagine a hand manipulating this object. There are lots of different contacts that can happen in different places at different points in time. In general, when you're searching over a discrete combinatorial large space, that's a bad idea. And what you want to do is you want to come up with some kind of relaxation methods that makes the search continuous and speeds it up. So this method is basically a domain-specific relaxation method. So here's how it works. We relax the thing a little bit. So we're going to search for a sequence of configurations denoted Q and a sequence of contact forces denoted F over time. So these are going to be the things that our optimizer tries to compute. Given those, it's going to compute a bunch of internal quantities, form a cost function, then do a gradient descent based on it, basically. Specifically, the way we do it here is this. So these are general equations of motion. This is the joint space inertia, acceleration. These are Coriolis, centripetal, gravitational, passive forces and such. F are contact forces. This is a Jacobian relating velocities in joint space to velocities in the space of the contacts. This whole computation is called inverse dynamics. So the idea is that if you have a trajectory of forces and positions, you can recover the control signals. Then you plug them into a big cost function, which basically is a kind of hand-waving equation, but you get the idea. So the task cost is the thing that tells you what you're supposed to do. For example, move your head forward or get the food in your mouth, that sort of thing. Control cost, you always put that there. That's some kind of regularizer that, in principle, it tells you to minimize metabolic energy and such. In practice, it's really good for regularization purposes. So it's a very good idea to put it in. You want to model the fact that you don't fall to the ground, etc. And this is the key term that makes this work very well. So this says that the normal force times the contact distance should be part of the cost function, and continuation is something I'll mention in a moment. So if the contact distance is 0, you can apply contact forces. If the contact force is 0, you may be some distance away. In both cases, the cost is 0, but you can have a situation where you're at a distance and you're still applying a force. So that's almost like a Jedi Knight that does that, and those flowers fly away. Why would you want to do that? So we found that even though at the end we want to come up with a physically realizable movement, it's not a good idea to constrain the optimization to space of physically realizable movements, because it's a very nasty, curved, discontinuous, bad space to optimize over. So that's what relaxation has to do with. We allow wishful thinking, basically, early on, and then we make it more and more expensive. That's where this continuation parameter comes in. So this is a scalar, and you change that scalar over the iterations of your optimization method, and in this case, you make it bigger and bigger. And so basically, early on, we're saying, okay, do whatever you want, just pretend that you're getting the job done. And then later, we ask the thing to really get the job done. So with this same algorithm, we've been able to generate a surprising range of rich and complex movements, which I'm going to illustrate right now. This is the wishful thinking early on. The blue thing is like what the thing is thinking, and then we increase this accuracy, physical realism cost, and then it's forced, the optimizer is forced to find something that has sort of discrete contact events that make sense, and then we just play the whole trajectory. So here we're given the initial condition of the character. This cross defines the cost function. Basically, the cost function says, please put your torso over the cross at the end of some number of seconds, and keep the velocity small in this case, and under that, do whatever you want. We don't care, just get the job done. Okay? And you can see that just by changing the initial configuration or the cost function. So here the cost function says, go over the cross upside down. Here's the same cost function, but we put an obstacle in the environment, and the thing has a physics model, so it knows about the obstacle. If you make the obstacle slightly taller, it uses both its hands and legs and such. This is a kind of a shared brain control. Here the cost function says the object has to go down on the cross, and the thing figures out how to use two characters to coordinate them. Here the cost says that the little guy has to put his head up, and it finds a way to make the big guy help him. Here the cost is about the object. It says, whatever you want to do with your hand, just make the tip of that object trace the outline of that square. And so it invents grasping and lifting and pressing and all that. Here the cost says make the object spin in the vertical plane. It invents all the contacts with the hand and all that. Same cost, but now the hand has fewer fingers, so it can't do the same thing anymore. Now it's forced to use that support surface, and it realized that it should do that.
I think that people can be confused because we are so used to computer animations that look much better than that. What is really the difference here?
Right. So almost every computer animation you have seen is based either on motion capture data or on a bunch of animators at Pixar sitting in front of a display with literally hundreds of control knobs and tweaking them and making the movement look really, really good. So this is qualitatively different from that. At the end, it kind of looks similar. It looks good. But the difference is that this is produced from first principles just by basically specifying these high-level cost functions in about 5 minutes of CPU time without any human intervention whatsoever, which obviously is bad news for the animators at Pixar. So this was sort of a cartoon model of physics. Then we decided to make this more biomechanically realistic. We put in sort of more detailed model of skeletal dynamics and a specific model of muscle energy consumption that people in the biomechanics literature have come up with. We also modeled muscle tendon actuators, so muscles tend to be connected to a skeleton with both series and parallel elastic elements, and there are things called hill-type models that are phenomenological descriptions of how muscles work, but they're pretty good ones, and they've been around for a long time. So in this case, one thing to keep in mind is that if you have a joint and a muscle tendon actuator attached to it, you don't actually know how long the muscle is just by looking at the joint angle, because the muscle and the tendon can stretch relative to each other. And that actually introduces another dynamic variable in there. On top of that, the muscle activation, particularly the calcium sort of concentration inside the muscle, is yet another state variable. So here we're optimizing for all of that as well. I'm going to show you movies in a moment. Here is walking. So these are a few joint angles of the knee. These are joint torques. These are some muscle activations. The dark red lines are what the model does. The pink lines are averages over some very large data set of humans walking on treadmills at Stanford from Scott Delp's lab. We have not done the mechanical Turk intercultural study that Shimon did. So this is just Stanford. Same thing for running, not so accurate, but again, this is a model that knows nothing about the brain. It just says you have a body, has a bunch of muscles, this is how they consume energy, please move forward. We don't know how. And the same model can generate a range of other behaviors as well. Here's walking. Here's a zoom in on these muscle tendon actuators, so you can see how the relative length of the muscle tendon changes, and the red, when it becomes red, that means the model decided to activate them. This is running. Notice how the upper body is rather stiff. That's because we ran out of time and we didn't put muscles in the upper body. And so this is kind of an incompatible cost function that prefers to use the legs, basically. Here's walking on various inclines. Here's jumping. So all of these are very simple cost functions that have the metabolic energy thing that somebody else did 15 years earlier. We have not touched that. And some kind of state cost that says, for example, your leg has to pass through that point with some velocity. Okay, so this is a great example of sort of biomechanically realistic models built from first principles, but obviously this is done offline, right? So far what I told you, that trajectory optimization can produce surprisingly rich and complex movements. The optimization methods themselves are actually generic. So these used either LBFGS or Gauss-Newtons methods. The trick is how we handle contacts and how we do this continuation and contact smoothing. Optimizing this additional wishful thinking forces that I mentioned that turns out to make the methods really powerful. On the downside, we need about 1,000 iterations even of a second order method. So 1,000 iterations of Newton's method is actually a lot. Usually when you use Newton's method, it either converges in 10 or 100 iterations or never converges. So this is actually kind of an unusual situation. All our software is very highly optimized, so this runs in about 5 minutes of CPU time, but still it's not real time. Meaning that in each of those movies, I had to specify the initial position of the body, and it spent 5 minutes thinking and figure out what to do in the next 5 seconds. But if you have to stop and think for another 5 minutes, that's not good. So how do we go to real time? So I'm going to present two ideas of how you can go to real time. The first one is one of the oldest tricks in the control theory book. It's called model predictive control. It's a very simple idea. The idea is the following. We're basically going to do trajectory optimization, but we're going to do it in real time. That's very ambitious. We need a really fast optimizer, but computers are fast enough and our software is good enough, so it actually works. Here's the high-level idea. Suppose you're here. You're going to plan optimal trajectory over some horizon, which is limited because you cannot compute that far ahead. And you start executing the locally optimal feedback control law that your planner gave you. Except the world is evil and wrong, and well, your model is wrong, the world is correct, but same thing. And so the reality diverges from what you planned, but it's okay because sometime later you're going to sense what happened, plan again, and keep executing. So what happens is at each point, so you basically have this bundle of plans that are kind of stretching into the future and steering you along the righteous path towards goal achievement. Mathematically, the way you do it is at time t, you're going to sum up all your running costs from time t to some horizon t plus n. And then at the final point, you can actually apply some heuristic approximation to the optimal value function. What's that? For example, if you have a chess playing program, optimal value function is a heuristic that tells you how good is a given board configuration from your perspective. It's not exact, nobody knows what the thing is. A bunch of chess experts got together and tried to cook it up. If you act greedily with respect to that, it's a bad idea. You end up with a very weak chess player. But if you have a fast computer that can look through the chess dynamics for a few moves and then you act greedily with respect to the same heuristic, all of a sudden you get a qualitatively better player that can beat any human. So that's kind of the same thing we're doing. We're basically playing chess with physics in real time. Of course, many details are different, like this is a continuous optimization problem. It's not actually a tree. We can explore all the branch and bound and clever tricks that people do in chess. They don't work here, but on the other hand, we have gradients and Hessians, and that's a good thing. So let me show you a few examples of this thing working in practice. This is the simplest thing we actually started with. So here the cost function says that this ball has to come back to where the paddle is. The balls are wrapped in reflective tape, and there's a Viking system looking at them and thinking they're markers. This is something called an acrobat. Here's a little snake-like thing. So here the cost function says that the nose has to go to the green thing, and please stay away from the red thing because it's bad for you. And it gives rise to these emergent behaviors. Here the cost function says keep balance, basically keep the body over the foot. This little thing here is a force sensor that we used to basically reach in the simulation and perturb it. Balance cost again, but now it's a much more complicated thing. And this, by the way, works in real time on a 6-core processor. Here's a very violent external force that we're generating. And the thing invents what it needs to do in real time, basically. It's like a ninja of some sort. So the same algorithm with some small technical adaptation was. Oh, hold on. This is interesting. So here we're planning for one model, and then we're executing in a different model. So this is our physics engine. This is something called Gazebo, which uses the OGE simulator. Here the cost function says keep your head pointed at that phantom head moving around, and think figures out how to balance. So here the cost function says the object has to go somewhere in space. Do whatever you want with your hand. And again, now this is planned and executed in real time. So you can see here that the thing is doing pretty bizarre things with its fingers, and actually there are no biomechanical constraints in this hand, which is why it can do a lot of things that your hand cannot do. So everything I showed you so far is in simulation, except for the little ball bouncing thing. That's actually a very simple system. When we started to apply this thing to physical systems, we're just getting there, really. But as you would expect, there is a difference between our models and the physical world, and that makes bad things happen. And interesting, this is something that people in neuroscience rarely care about. I mean, because we study the brain as passive observers, and the brain works, like we don't have to worry about making it work, we just have to write papers about it. And that gives us the luxury to ignore a lot of really hard problems. For example, there's a brain there, it has some sensors, and it's building some models of the world, but what if these models are wrong? How does that affect behavioral performance? Well, if you put it on a robot, it becomes immediately obvious. So here we discovered, for example, here the task was to use 4 fingers. These are basically haptic devices called phantoms. We use them as fingers of a phantom hand, for obvious reasons. The task was to hold this thing in place, and then we wanted to be able to specify the position and orientation of this object in space, and we wanted the thing to invent, what to do with the fingers and how to position it everywhere. We're not nowhere close to solving that. I mean, we can solve it in simulation, but not in reality yet. Here's an example where we ended up cheating. We basically put this lid here. Here's us with the sensor specifying where the thing should go. One good thing about this small operative control business is that it's very resistant to perturbations because it has a plan, but the plan changes every 25 milliseconds. So it doesn't really care how it got to a specific place. It just says, okay, I'm here. I don't know why I'm here, but I'm going to do the best thing from now on. And so you can do really bizarre things that nobody ever does in robotics, like go in and move the base of the robot while it's operating. But we can do that here. So now, as you might suspect, the optimization that we're doing here is much more aggressive, right? Where before we spent 5 minutes of CPU time finding a nice, beautiful trajectory that looked like a Pixar animation to some people. And here we only have about 20 milliseconds of CPU time to come up with a trajectory. So what's going on here? Two things. First, the key to making this whole thing is to use warm starts. So when you plan this trajectory and the time advances here, you're not going to optimize this trajectory from scratch. Instead, you're going to use the previous solution to warm start the optimizer, and then you're actually going to have only one step of a Gauss-Newton method. Why one step? Because you ran out of time. In fact, if you had the time for multiple time steps, the optimal thing to do is probably to just still do one time step, execute a little bit, see what happened, and then replan it. So my guess is that we're always going to be in the regime where we only run one time step, and we're just going to make the time steps shorter, the horizons longer. So anyway, that's one thing that's happening, but there's one more thing that's happening, which is that we were forced to do a certain amount of cost function engineering here. What I showed you before with these characters climbing on top of each other, that was really simple-minded cost function that says, here's the end goal, simple possible quadratic around some spatial goal, plus metabolic energy, go do it. 5 minutes of CPU time, we'll have the answer. Here, because the optimizer doesn't have that much time to run, we have to help it. And we do that by handcrafting more clever cost functions that are somewhere in between cost functions and heuristic value functions in some sense. And after doing that for a while, we realized that that's actually a lot of work. And so we developed a formal language for expressing cost functions so that we can engineer them very quickly. And this seems to be a general way to represent cost functions. So you have states and controls. You're going to define some features of them. And what are these? Well, these are basically any static function you can compute. Our physics engine computes a bunch of things, so you can use those. Okay, so these features can have reference values that you get to specify. You subtract them. If there are things like quaternions, you subtract them carefully, but nevertheless. You define a notion of a residual. Residual is something that should be small, so we apply some vector norm to it. Norms are things that take the vectors and turn them into scalars. And then we mix them up with some linear coefficients and call that the cost. Okay? And then we have this language, which is an XML file that allows us to reference different parts of the physics computation, define features, references, norms very quickly. We can define these coefficients. So you edit this thing to define a new cost function. And then when you load it in our GUI, it actually exposes all the coefficients, and you can play with them in real time. So now you have this real-time environment where you can actually tweak the cost function in real time and see what that does to the behavior. Let me illustrate this. So this little guy here is a unicycle. It can put torques on the wheel. And the mixture of cost which says keep energy small, keep the body over the wheel, don't wobble too much, and there's another cost that says reach, but it's disabled right now. So these are different terms. Now we're going to change the balance cost. We're going to increase it. And see how the behavior instantly changed. Because now it knows that it shouldn't move the body relative to the wheel, so it starts using its arms to achieve whatever the composite cost is. Now we're going to reduce that, and we'll tell it to reach. There's a target outside the screen that you cannot see right now. So now we increase the weight on the reaching cost. It has to think for a while. That's interesting. So when its head is red, that means it got a headache because it knows that things are not looking good for it because the optimizer is giving it a high cost. And so notice what happened here. After we turned this on, it didn't start driving immediately. It had to think for a while. And then it switched to driving. Why was it thinking? Because it was running more trajectory optimizations. Okay, and then happily it reaches to the target, and now things are good. So reaching movement, like we started with, but more than a point mass. I should say when we start applying these things as models of how the human body moves and how the brain controls movement, and we use optimal control theory, optimal control theory is not really a theory. It's a meta theory. It's kind of general framework for deriving specific models. And in order to make the model specific, you have to decide what is it that you're actually optimizing. And you could be optimizing many things. For example, if you want to have a universal curve fitting mechanism derived from optimal control, here's what you can do. Collect any data that you want, define a cost function which says I want to reproduce the data, so put a quadratic around the data, and guess what? The optimal solution is to reproduce the data, right? So just by saying that something is optimal, that doesn't mean anything. You really have to show that whatever you're optimizing was not just a curve fitting cost, but it was actually derived from first principles and somehow makes sense, just like every other model. So the cost function is the assumption behind an optimal control model. I mean, there's also optimality, but some kind of meta assumption. And as I said, if to make these things work in real time, we have to do this sort of cost function engineering. If you see how the models, optimal control models of biological movement, people try to make them as simple as possible because we want simplest possible assumptions to give us the most interesting possible predictions. But if you start looking more closely, you realize that things are not that simple. So for example, there's a field called neuroeconomics, where people are basically trying to do that. They're saying, okay, both humans and other animals, we believe they're rational with respect to some kind of criterion that's ill-defined, and so let's go and try to reverse engineering it. And they have the tricks with indifference curves and all kinds of experimental paradigms, and then there's discounting, multiple things you might care about, etc. So determining experimentally what these things are that the brain cares about is far from a done deal, but we have the machinery to optimize them, whatever they are. So kind of have the tools to build interesting models. So anyway, so that was one approach to taking these optimization ideas and running them in real time. Now there's something, I mean, it's impressive that this thing works, but there's something undesirable about this, which is that this is basically reinventing the wheel every 25 milliseconds. Right? I mean, this thing knows physics. It knows what it's supposed to do, and there's no learning whatsoever. You know, it may have done this 1,000 times before. Next time it does it, it's going to reinvent it from scratch. So obviously we don't do that. So now the question is, how can we use this machinery to generate training data for something that's going to learn from it? Okay? And another recipe in science, if you see a bandwagon, jump on it while it's still going. Bandwagon is a deep network, so we're going to do deep learning. Apply to control. I'm going to point out a couple of sort of unusual things we need to do to make this work for control in the control setting. So first of all, this is going to be a network that's going to be interacting with the body in real time. So the network plus the body is a recurrent, is a dynamical system that has its state. We're actually going a step further. So the state of the system are the positions and forces in this case, and the activations of some small number of neurons that we're calling recurrent neurons. And then this whole thing is going to be the input to a big feed-forward network with 5 layers and a total of 250,000 units. And that's going to tell us how everything should change over time, and then we integrate it and we run the dynamics. So the architecture of the network here is kind of interesting. It has it's like a big feed-forward layer that goes and feeds into itself, but all the recurrence is limited through a very small bottleneck of about 10 or 20 units. Okay? That's not because we read Tali's paper on the information bottleneck, although we should, but for very simple engineering reasons. And the engineering reason is that when you create a recurrent network, the activities of the units become part of the state, just like your joint angles and velocities are part of the state. If you're going to do trajectory optimization, you now have to optimize trajectories over some very high dimensional state, and we don't want that, so that's why we want to keep this having low dimensionality. This can be as big as it wants because it's just a static mapping. Okay? So now we do optimization as follows. We break the optimization into 2 pieces. One is the network training, which is just supervised learning, very similar to what you see in vision. The difference between vision and control is that in vision, people have the luxury of having huge data sets that are already available on the internet. In control, we don't have that. If you think about what is control, well, control is the business of making movements happen. Like, the reason we're doing it is because we don't know how to move yet. Well, if we don't know how to move yet, we don't have the data. Right? So it's a bit of a conundrum. So what do? Well, we use trajectory optimization to synthesize the data, and then we use the synthetic data to train the neural network. What I just said doesn't work very well, as I show you in a moment, and instead you actually, because the problem is just too hard for the network. So it turns out we actually have to do something else. We have to couple the network training and the trajectory optimization. So instead of using trajectory optimization to build one ideal data set that we learn from, we actually use the trajectory optimizer more as a teacher. And so to understand that, suppose you want your kids to learn calculus, right? Do you teach them calculus in first grade? The answer is no. Why not? I mean, that's the thing you want them to learn eventually. So why don't you just teach them calculus? Well, there is something about the human brain that says, well, if you want to teach me X, you should actually teach me Y first and eventually teach me X. Something like that seems to be happening with those neural networks. If you ask them to learn the ideal thing, they get actually stuck in bad solutions. So what we're doing here is this. We initialize the network somehow. We see what it does. Then we take those movements, give it to a trajectory optimizer. And our trajectory optimizer has a mixed cost function. And that cost function says, solve the task, but at the same time, stay close to whatever the network happens to be doing right now. Okay, so have this mixed cost. So the trajectory optimizer is acting like a teacher, kind of gradually pulling the network towards better and better solutions. And that turns out to work a lot better. And I'll show you a comparison later. This takes quite a lot of computing, so we do that in the cloud. That's what the cloud looks like. We use one GPU and a large number of CPUs, 30 of them. The reason we use CPUs is because trajectory optimization and physics simulation is much better suited to a CPU architecture. Another thing I should mention is, for those of you who are hearing that GPUs are very powerful, that's a bit of a misnomer. If you count the number of transistors, it's about the same. They're powerful at different things. CPUs are really powerful at complex code with a lot of control branching, need for a lot of cache, things that GPUs are very bad at, and vice versa. So the computation having to do with physics simulation and trajectory optimization is actually a much better fit for a CPU architecture than a GPU one. So we have a large number of those optimizing trajectories for us, and then we feed them into a GPU that's training the neural network in a supervised fashion. I said that's how big it is. It's very fast compared to the vision things that take a week to run. This only takes about 2.5 hours. The network is also smaller. It's about maybe 10 times smaller, but still, we're getting rather drastic sort of improvements in speed. Now, we have to give it a rather diverse training set if we want this thing to generalize. And so the way we do it is we have some initial conditions for our character, and then we give it spatial goals somewhere, and then as the trajectory optimizer is finding a trajectory, we pick some intermediate state as another initial condition, give it some other goal. So we design the library of cost functions to kind of span, it's like to build a tree that kind of spans the behavioral space that we care about. Another really important thing we do is something that in the neural network literature has been called tangent propagation. In optimal control, it simply means learning the feedback gains. So what I mean by that is that if you have a neural network that you give it some input as a state and it gives you an action, right? That's just the nominal output. The question is, if you change the state a little bit, how should the action change? Right? That dependence is given by the feedback gain. And our trajectory optimizer is actually telling us what the optimal feedback gains are. And so we use that knowledge and train the neural network on it, and that helps a lot. Okay? So with all that said, let's just see some movies. Here's a jellyfish. So the inputs are, again, the states, a few recurrent neurons. There are these things that are going up and down here, and a target, which we'll get to move with a joystick. It's the bird now. And we can make it follow the target and turn around, etc. So again, this is a completely autonomous system after training. The only thing under our control is the target, and then we can make it do all kinds of things. Here's this little humanoid. We can make it step sideways and walk forward and backward, etc. Now, this could actually run a lot faster in real time because evaluating the neural network costs nothing. We can change the morphology of the body. I should say everything I'm showing you is exactly the same neural network architecture, same learning algorithm, same everything, just the body morphology changed. Here's how your sofa might walk if it had feet. Here's a donkey-like thing. You can make this thing walk sideways. I think there's a turning coming up later. What else do we have? To have a spider of some sort. This is an illustration of the little trajectory pieces that the optimizer is computing. Like there are thousands of those that are being fed into the network. And they span enough of a space such that if you learn those, then you can generalize and do all these other things. If you compare this to a version of model predictive control that we can do here, what we find is that, that's something that actually we've observed about model predictive control all along. As I said, remember, model predictive control is this real-time trajectory optimization. Because that thing like invents what to do all the time, it doesn't give rise to very regular motions. It can decide to do the same thing in very different ways. Because we're training a network to do that, the network has no choice but kind of regularize the behavior. So for things like walking or other periodic motions, the network actually gives things that look better and they seem more reasonable, although they don't necessarily have a smaller cost. Here's this comparison I mentioned earlier. If you do the joint optimization is the regime I described where we use the trajectory optimizer and the network trained in an interleaved way versus separate optimization, which means that get an ideal data set of movements and train on that. So these are learning curves. This is the optimization epochs over, log training errors. So joint optimization looks like it has better error, but this doesn't tell you the whole picture. The important thing is this. So this is joint optimization. This is what we do. Optimal is the things that we've optimized and they look the way they're supposed to look, and then we actually roll it out and run forward dynamics. What happens is really what was supposed to happen. If we do a separate thing, we can optimize something shown in red, note this y-axis change. But then when we roll it out, the resulting dynamical system becomes unstable and bad things happen. So in general, this is another difference between control and things like perception. Control is ultimately about coupling the thing that you're learning with the world and the physics and getting feedback. So if you do vision, like people test recognition performance, right? So you get something wrong, well, fine, it hurts, it costs you a point, but then the world resets and you get another image, nothing bad happens. If you're doing control, what happens if you do something wrong, nobody's going to reset you. You're going to remain in the same place while your control is doing the wrong thing, and things are going to get worse and worse. Maybe you're going to get unstable, maybe you're going to fall. So it's almost like a research competitor who tests your algorithm, finds some kind of input where your algorithm doesn't work well and just generates more and more of those inputs and makes you look really bad. That's kind of the type of problem we have to deal with in control. So it tends to be sort of a more sensitive thing. Now, let me just say a bit more about our robotics efforts. So like I said, we want to push these towards physical systems. And one way to do that, actually, let me switch to the next slide. Well, one way to do that is to do careful system identification, which basically means identifying the parameters of the model so it fits the real world. That's something we're doing. So for example, here's the system we're playing with. This is a phantom robot playing with a hanging cylinder. We're actually teleoperating it. And it's instrumented with all kinds of sensors, so we collect the data. And then what we're doing is turns out we want to estimate the model parameters, but at the same time, we have to estimate the trajectories of the whole system. And it turns out that these two have to be treated as a joint optimization problem, which is very unfortunate because it's a lot harder, but we found that to be necessary. And the reason is because something like that happens. So if you consider this axis to be the model parameters, like the contact softness and the masses and joint axis and so forth, things that are properties of the system but remain constant over time. And on this axis, you consider the movement trajectories. So there's a lot of data here, a little bit of data here. The joint fitness cost in terms of fitting the data seems to be something very elongated. So if you fix the model parameters, do the estimation, fix this estimation, try to improve model parameters, you get this really nasty chattering that takes a long time. So you really need to treat them jointly, it turns out. When you do that, you can so here's a movie of the estimated thing. And this shows you a few joint angles and joint acceleration. So gray is data and red is what our model predicts. So what we're trying to do here is, obviously I'm skipping a lot of details, but we're trying to build a physics simulation where we can fuse all the sensor data and all the command signals that we generated and our best model. And we want that physics simulation to make sense of absolutely everything that's happening right now. And if it can do that, then the hope is that if we plan through it and then we apply the control signals to the physical system, it's going to work well. So that's better modeling is obviously one approach to making this work well. Let me just briefly mention one more approach, which is this. So here what we're doing is we're planning for a little robot. Here's the cute little robot doing the same thing, more or less. So the way we're doing this optimization is something called Ensemble Optimization. What does that mean? Well, we have a model of the robot. We know it's not perfect. We can plan a trajectory for the robot. If we just play it blindly, it's going to fall. So here's what we do. We say, well, we have a model, but our model may be wrong. So we're going to generate 10 different models. have different masses, different foot shape, different whatever. And then we ask the optimizer to find a single trajectory that's going to work for all 10 of them. And the idea is that if you can find such a trajectory that works for 10 different models, then it probably works for everything else in between, including the real robot. Okay, so it's a way to robustify thank you, these plans and run them on the system without actually modeling the system well. So this is kind of a stopgap measure. I mean, what we really want to do is build good system models. Okay, here's a simulator that there's a website. You can play with it if you want. And I should kind of end. So let me end with a little bit of philosophy. Philosophy one. Making an algorithm biologically plausible tends to reduce its performance. It's really sad. So if you take vision, for example, actually Shimon Ullman's talk was a great example, but if you look at those convolutional neural networks, there are a few things that you have to do to make them work well. So one of them is something like divisive normalization within layers. Actually, if you talk to Jan LeCun, he'll tell you that this is the one inspiration he took from biology. It's sort of the human weasel story, and that's good. Weight regularization, things like dropout, L1 regularization, whatever. This is neutral. I mean, you have to do that with every statistical model. But there are a bunch of other things, convolution, for example, meaning that you apply the same filter everywhere, and that means lots of neuron pairs have to use the same synapse. That doesn't happen in the brain. Backpropagation to compute gradients, obviously doesn't happen in the brain. The fact that this thing is feed-forward as opposed to being recurrent, that doesn't happen in the brain either, right? Now, the point is that if you take out any one of those red things, we would not be talking about deep learning today because it wouldn't be working so well. So they're kind of essential from an engineering perspective to make it work, and yet they have nothing to do with the brain. And in general, we seem to have two classes of system-level models of brain function. On the other hand, we have models that work in the sense of solving hard computational problems, but the details are wrong, or at best, they're left unspecified. On the other hand, we have models that fit some selected details from the experimental literature, but they don't actually work, meaning that you couldn't really compute anything with them in interesting settings. And ideally, we should bridge the gap between those. And I don't know how to do that. But with regard to specific algorithms I mentioned, I want to make 2 points related to physiology. Now, all these algorithms I talked about spend almost all of their CPU time in evaluating the physics model. This is done for purposes of finite difference approximations to derivatives, or just sampling or training and so forth. And then the actual optimization, everything else takes, I don't know, maybe 10, 15%. So there's a lot of computing power that actually goes into physics modeling and internal simulation. Now, if you look at the brain, people are talking about something called internal models, and the motor control literature is full of those. And that's supposed to happen in the cerebellum. There's plenty of good studies suggesting that. Interesting thing about cerebellum is that it actually contains most neurons in the primate nervous system, like 2/3 or something like that. And yet the existing views of what the cerebellum does do not really explain why 2/3 of your brain should be there. So remember that box diagram that Nikos Logotheris showed yesterday? There was like memory thing and there was the cerebellum. Like if you had a functional diagram that was proportional to the amount of neurons, the cerebellum should be that big, and everything else the brain does should be that big, right? So we really need models that kind of get there, and these algorithms, not by design, but they just happen to have that feature. The thing that cerebellum happens to be doing is the thing where we need to invest almost all of our CPU time to make this work. In terms of representing movement trajectories, which is what I was doing, is that plausible? And I wouldn't necessarily argue the brain is doing it, but what I would argue is that if the brain wanted to do it, it could without contradicting any data we have. In particular, there are two ways that you could do it implicitly. One is that you can have different neurons representing motor behaviors at different times in the future. And that's actually observed. So if you look at motor cortex, people have correlated the neural activity with movement at different times in the future. And there's actually a surprisingly broad distribution. And this feature is very long compared to the transduction delays that you can measure just by stimulating and recording muscle activities. Another idea popularized by Mark Churchwant and Krishna Shenoy and colleagues is this idea that thinking of motor cortex in particular, some kind of dynamical system, and thinking of motor planning as setting the initial state of that dynamical system and then just running it forward and then just unfolding the dynamics corresponds to execution. And so the idea there is that you actually represent an entire trajectory implicitly just by specifying the initial state of a semi-autonomous system. So that's some kind of very compressed representation. Not clear how you would do any sort of explicit planning with that sort of thing. It's almost like trying to do data analysis on a zip file without ever unzipping it. But on the bright side, this representation is unique that it can simulate itself, right? Because it's actually interleaved with the notion of dynamics. That's my own alarm. So that's that. Thank you for listening.